So now let's get some practice in drawing free body diagrams. So I want to say first that this skill or tool of drawing free body diagrams is absolutely essential before you take the FE. So know how to draw free body diagrams before taking your FE exam. Because we know this is applicable to statics, most importantly. Like statics is number one where we see this stuff. Then you apply it in dynamics, although those have free body diagrams and the kinetic or dynamic diagrams, which I will do a video in the future for dynamics free body diagrams, but the general idea is still the same. And you also have it in mechanics and materials, right? Even fluid mechanics for hydrostatics. And also when we're looking at civil, you have it for structural engineering or structural design, steel, concrete, and when we're looking at those beams. Even for mechanical engineering, mechanical design, right? You have to know how to draw that free body diagram. So this skill will take time to develop, and if you've been out of school for a while, don't worry, just apply the rules we discuss here and do plenty of examples and make sure you just practice, right? Get a lot of practice in, and I know it took me years just to fully master this skill. But we know the goal is to have that free body diagram, and if you have it with all the forces on it, the weight force, the tension, the spring force, the normal force, it just gives you that confidence. Okay, I drew the correct free body diagram, then I'll just apply what we normally do. Like for statics, some of the forces must equal to 0, whether in the x, y, or the z, whatever, right? And for dynamics, F equals ma, Newton's second law, based on that free body diagram. So if you have that incorrect or you miss a force, it just makes things complicated and will probably give you a headache. So let's get some practice in, and this is what we'll do here. And I just want to say that if you want this PDF, just go down below, drop your email in the link, and I'll send the PDF directly to your email, just in case you want to practice this before you see me do the solution, and try this on your own and keep up with me. You can print it and keep up with me and practice drawing these free body diagrams. So let's get to it. So let's begin one by one. So we'll start basic stuff at the beginning. So we have the loading diagram, and here we're asked, okay, draw the free body diagram. So we have this, and we have an applied force. It's a box sitting on a flat surface. So we want to draw the free body diagram of box A, right? So what we will do is, you can put just a point in space here, but I just like to redraw the box. And let me do that. You have a box, right? And note the box has a center of gravity. It's that center, right? It's the center. And let me just call that G. And that's going to be an important point because that G point, the center of gravity, is where we have the weight, right? So for the weight, I'll use this color. So let me use red for the weight. And that's going to be the weight of box A. And note how W is for the weight. A is like for the box or the object you're looking at. Sometimes you have multiple boxes, so I labeled that A, box A. So now that's the weight, and the weight acts down. And note, what's the weight equation? Weight equals mass times gravity. But in this case, we're not worried about putting numbers if you're given the mass, gravity. So we're not worried about that. We just want to draw the correct forces and how they act, the direction they act. These are like vector forces. So now that's the weight, and it acts down. Then we know the weight, if the weight acts down, this box is pushing down on the flat plane. There must be an equal and opposite reaction, right? If you push on something, you will feel something hitting you back, right? We call that the equal and opposite reaction. And in that case, if the weight goes down here, what's the equal and opposite reaction? It's going to be the normal force, right? And we will use that as green. And for the normal force, I usually like to depict it by just N. Some people use F sub N, whatever you feel comfortable with or whatever is a habit for you, but I'll do N. So that's the normal force. Then we have the force that's applied, that's actually drawn, right? And note, sometimes that force applied is like a rope or cable, but no, it's, in this case, it's still the same. It's a tensile force or a pulling force in this case. So we will say F, that's given. Then one last thing, let's just assume this is static. Let's assume it's static. For dynamic, avoid that for now, that's a later video. But if we assume this is statics, if you have a force pushing that box to the right, we have something acting down here, right? It's the frictional force. So we have frictional resistance, and we call that the frictional force. And I like to draw my frictional force as F sub F, or you can just use F, or you can, yeah, I always just do F sub F, frictional force. That one's the frictional force. And note the equation for frictional force, friction is fun, so it's going to be mu times N. Mu times N. And that N is actually the normal force, right? It's this. So that's the frictional force. It's like frictional resistance at the bottom here. You have some frictional resistance when we're trying to pull in that direction to the right. Frictional force. And that depends on the static condition. I just want to say that frictional, the static coefficient, not kinetic, assume statics, static coefficient, and that should be given to you in the problem statement. And note, frictional force is not really like a force, it's like a resistance. It's not like a pulling force or applied force, it's a resistance force. So that's going to be that free body diagram. We're basically done with that one. So now let's do the next one. Now the box A is at an incline. So this one is tricky. This one gets tricky. So we have box A. Okay. Let me draw it like that. And let me label the G, center of gravity. And that's going to be where the center is. And we know at G, there's always the weight that acts down, right? And the weight we will use red, same idea. So that's going to be the weight. Let me call it W sub A. So we have that, the weight acting down. Weight is mass times gravity, right? So we took care of the weight. And we also have some normal force, right? And note, the normal force will always be perpendicular. In this case, it was perpendicular, right, to the surface at the bottom. Same is true here. It must be perpendicular, and that normal force will act, the line of action of it acts at the center of gravity. So that's going to be the normal force. You have that normal force perpendicular to the incline, to the surface. So we took care of that. Then what else do we have? We have the weight, and one thing I forgot is going to be, you have no applied forces, and let's assume this thing is like staying there, right? It's just the equilibrium. We know we have to consider some friction, so it might slip down, right? There's that probability of it going down. So what I'm going to do is say you have some frictional resistance acting this way. Friction force, which is mu static times the normal force, same idea. And no, I drew that in that direction because friction is like a resistance force, and it resists the direction of impending motion. So think of it as the direction of motion, but when we say impending motion, is it about to slide down? Is it about to impend and slide down, or is it about to go up? So there's always that question, and that requires practice, but that's beyond this video. But think of it as simply the frictional force is opposing the motion, and we will say, okay, this box, if you look at it, because gravity acts down, there's the probability is it's going to go down. It makes sense why it would go down, because you have this acting this way, you have that, and you would break up those forces. But the frictional force, we will point in that direction, right? So now the other thing is, when you're looking at inclined planes, you want to reorient the axis. So I'm going to call this the X prime axis, and I'm going to call this the Y prime axis for inclined plane problems. Typically, we're dealing with just our normal X and Y axis, right? This is positive X, this is positive Y, up to the right. And we know gravity would act down towards the center of the earth. So that's just our regular axis, up and right. So now we know we want to reorient this and have X prime and Y prime. So X prime is going to be parallel to the incline, Y prime is going to be perpendicular to the incline, or normal. So doing that, things become interesting, because if I say this is my X prime, and this will be my Y prime axis, now we know, okay, you have to ask yourself, when you do equilibrium, or F equals ma, force of friction is acting along the X prime. That one's good, right? To our new axes. The normal is acting along Y prime. That one's good as well. But now things get messed up. The weight is acting using the old axis, right? just to the right and up. So the weight is acting just strictly down. We have to break up that weight component, which is acting down, to a component in the x prime axis and a component in the y prime axis. So what we will do is say we have a component this way in the x prime, so this is wx prime, and we have a component that acts this way, and this will be wy prime. So that's going to be how you break that up. And if I draw that on the side here, it looks like this. You have the weight at A, which is like the magnitude. You have wx prime, and you have wy prime. wy prime. And now, we know here, this is 30 degrees. Now, the tricky thing is, where is the angle here? Is it here, or is it going to be here? Or in other words, is 30 degrees here, or is it here? I'll tell you right off the bat, it's going to be here. 30. 30 degrees is always with your y component and the magnitude of the weight. Always. When you have an incline. There's an explanation for that, but simply put, let's say you have your original. Let's say real quick, if I explain this, you have your original x, y axis. This is the original, how we usually analyze things. But now what we did is went from the original and rotated 30 degrees to get to the new one, to get to the x prime, y prime orientation. So what I'm going to say is take the original and rotate it. We rotate the x-axis by 30 degrees, approximating it like that. We call that x prime, right? We have a new one, x prime. By how much? 30 degrees. 30 degrees counterclockwise. So we started here, went 30 degrees. So if I did that for that, you have to do the same thing for the y-axis. We take that y, rotate it 30 degrees, and that gives us the y prime axis. So that's going to be that one. So it would look like this. This has to be 30 degrees as well. So if I denote it like that, that has to be 30 degrees. So now we know if that's 30 degrees, this has to be 30, right? If you look at this closely, the weight is this. That's 30. This has to be 30. Think of this wy prime is the one going this way, right? This component. So that's 30, that's 30. So that's a way you can think about it. I know there's other ways, but I just want to practice the other free body diagrams. And if you have questions, please let me know. But that has to be 30, and you can always just memorize this. It's always with the y component and the magnitude, that 30 degrees. So that's how you draw that free body diagram for that one. So we're done with that. Let's go to the next one. This one's also a little bit tricky. What we will do first is we have the box A. So box A is going to be on top, and we want to draw the free body diagram of both box A and box B. So now let's do box A. We will say we have box A here, and it has a center of gravity. So we have the weight of A. The weight of A, right, at the center. You have this cable, right? A cable always has a tension force. So let's just use this color for tension. So it's a tensile force, and tension is always away, right? If you take a rope, how can you, if you just compress it, there is no force in it. You have to actually stretch it. So it's always away. Tension is always away in the cable. So now that's that, and we know this box A is going to hit the bottom, and it's going to induce a force on box B. Then box B is going to counteract it with a normal reaction, right? We know the weight here induces that weight force on box B, then box B hits it back with a reaction, and that's the normal reaction. So we have a normal reaction, and I'm going to be very specific and call that normal reaction normal AB, because it's the normal reaction between the bottom surface at A and the top surface of B. Normal reaction AB. So that's taken care of. Now we still have to consider friction, the frictional force. We're always going to consider that for these examples. So for the frictional force, we know, so let me use this color for friction. This, you can assume that the tension is trying to pull that box to the left, right? Box A. So if it's trying to pull it to the left, the frictional force has to go to the right. It will counteract that motion. So I'm going to say we have some frictional force here. We call that frictional force to the right, and we're going to call it AB. AB. between the surface A and surface B. So I denoted it like that. So now that's the free body diagram for the top box. Let's do the same thing for the bottom box. So that's a bigger box, so box B. So for that one, same idea. You have the center of gravity, and now we know we have a weight, right? The weight of B. So let me just draw that like this. The weight of B. Also, we know we have a normal force here, and that normal force, we know it hits box A, right? But also, it will induce the same normal force or reaction at this box B. But here you have to remember, in this free body diagram, it goes up. In the next free body diagram, which is down there, it must do the opposite direction, right? It must go down. You have to be consistent with that. So if you drew it up again, everything's going to get messed up. The signs get messed up. So here, in this free body diagram, we drew this normal force going up. In the next free body diagram, which is the one for B, it must go down. So you have to draw it down for this one. And it's the same one. It's the normal AB. Normal AB. And it's basically the weight, right? It's the weight of box A. But I just like to draw it as the normal AB because it's being induced between those two surfaces. It's at these two surfaces. It acts on A, but here be careful, we drew it up in the free body diagram for A. For the free body diagram for B, you have to draw it down, equal and opposite direction. So that's done. Now, same idea for this. Same idea. This one, the frictional force on the free body diagram for A went to the right. It's not going to go to the right on this one. It must be same magnitude but opposite direction. So what happens when we draw it on the free body diagram for this one, it's going to go this way. So it's the frictional force AB between the surface at A and the surface at B. So be careful and be consistent with that part. That's the trickiest thing. So now we're done with that. And at the very bottom here, let's look at the bottom. We know we have the normal force. So I'll draw it a little to the side here. But we know the normal force would act at the center of gravity. So that's going to be the normal force at B down there, right? And one last thing, this down there, you have also friction again. So we have a frictional force, and we will say that's going to go to the left. So imagine like these boxes, you can imagine them stuck together and they're both trying to go to the left. They're being pulled by that tension. So what we will say, it's going to go to the left, and that's going to be the frictional force at B at the bottom, right? At B. So let me denote that with a different color, not to confuse us. So that one should be, let me use actually this color. I'm running out of colors. Let me use this one. This one will be good. So that's going to be the frictional force at B, and it's going to go to the left. So now let's do some harder ones. So this one, we have a beam with a distributed load. It's a linear distributed load. We have a pin. We have a roller here. So okay, we will say we want the free body diagram of AB. So I'm going to draw the beam here, and we're freeing the body, right? That's the whole idea. We free the body from its surroundings. Then we will ask, okay, we have point B here. What's acts at B? We have the pin, right? Pin connection. So that one's going to be a reaction in the Y, BY, and BX. So always remember, for a pin, you have two reactions, one in the X, one in the Y. Because if you imagine it's a pin, so it's allowed to rotate, that means we have no moment reaction, right? We have no moment force developed. So we have no moment. But if you imagine this beam, try to pull it with respect to that point B, pull it like strictly in the X, it's going to have some resistance, right? And we call that the reaction. The reaction developed because you pull it with an action, there's an equal and opposite reaction in the X, right? That's what we call BX. Same idea for the Y. You pull it in the Y with a action, there's an equal and opposite reaction in the Y. But the direction doesn't matter. Just remember, you have to note you have two reactions for a pin connection. And if you get a negative sign in your answers, it just means you assumed the wrong direction. But when you get a negative sign, that's important for trusses and stuff. just carry that negative through all your calculations when you do practice questions. But note 2 reactions for a pin. So now we have a distributed load. How would you draw that on the free body diagram? So the best way is to actually just use 1 point load. But some of us may broke this down into 2 triangles, maybe did like a load here, let's call it P1, and did a load here, let's call it P2, and drew those 2 loads at the center, right? Like this is the center of gravity of that triangle, center of gravity of that triangle. But that would be the long way. You still can do that, but it requires a lot of work. There is a shortcut when you have a shape like this. It's like a whole triangle, right? And it's symmetric. Basically, you have 2 right triangles. They're symmetric about each other, or they're mirrored about the center line. And the best way to actually draw this would be to denote it as just 1 point load. So you can just draw it as 1 point load that acts at the center, P. And it's always going to act at the center of the beam. In this case, it's going to act at the center of the beam. So it's going to be P. And simply put, that P, you can get it as the area of the whole triangle, this whole triangle. And the area in this case is going to be what? It's going to be 1/2 the base. What's the base? This is the tricky thing. The base is going to be the whole length. So be careful. It's not just the base like this. It's going to be the whole length. So let's call it L. And let me denote that here as the whole length of the beam, the span length. And we have the omega, or the W, is going to be what we put for the height. It's essentially the height like that, right, of the triangle. And that's the best way to do it. Just know it acts at the center. So we're done with the distributed load. Last thing is at A, you have a roller, right? Rollers always have normal reactions, or reactions strictly in the Y. I like to think of it as normal reaction because they're always going to be perpendicular. So a roller only has a reaction in the Y. You have to remember that. So now for that roller, we know we have a normal reaction, and this thing sits on an incline that's complicated because it's inclined, right? It's not just flat. So the normal reaction is going to act like that, right? So the way we would draw that is at an angle, because normal reaction is always perpendicular. And I'm going to call it the normal at A. Normal at A. So now it gets a little bit more tricky because this is a 3, 4, 5 triangle. And what I'm going to say is denote the angle here as theta. So you can't see that good, but I'm going to denote the angle with the hypotenuse side and the x as theta. That angle. So now, when you have something like this, you just always have to remember what we applied above for the angle. When you have an incline, it's the same idea. But here, I just want to save time and tell you, it's always going to be the one with the y component. What does that mean? We know this normal reaction has an x component, a y component. Let's call it NAY. And it has a component in the x, NAX. So we know here, I just said, remember, that theta is always going to be with the y. Always. It's going to touch the y and touch the total magnitude, or the hypotenuse. So I'm going to say it's this. It's the same idea of what we did, right, for the incline. And it's going to be here. Theta is going to be that. So if theta is that, how would you draw 3, 4, 5? Let me draw a triangle here, a small one. Theta is this, right? Theta has to be that, and we know theta is here. The adjacent side is going to be 4, and the opposite side here is going to be how much? 3, and the hypotenuse is going to be 5. So no, that's how I would do that. Just remember, when you have stuff like that, almost like always, it's always with the y. It's always with the y, but the same general idea of what we discussed here is going to be applicable. This idea, it's the same thing. So that's going to be a tricky one. You just have to remember that. And it's not, if you have it flipped, usually I do that, but think of it as the opposite of what you would normally think when you do this. It's always with the y component, and the hypotenuse is where theta is. If we know where theta, we can draw that 3, 4, 5 triangle. So that one is done. Let's keep going now and do this one. So this one, we want to draw the free body diagram of the pulley at D. So this pulley at D. So simply for that one, you just draw a circle we have point D here, right? Point D, and you have this is going to be what? It's a cable, so it's going to be tension, right? So that's going to be a tension force, tension, and this one is also a cable, but it's inclined, right? It's a tension force, tension. And we know here it's a 1, 2, and you can guess the hypotenuse, do Pythagorean theorem, right? And we know the tension force here, it's the same for a pulley. So that tension force is the same. This tension is the same as that tension. So that's how you draw that for D. Let's do the free body diagram for the cylinder now. So cylinder, you have it. What does a cylinder have? It has a center of gravity and it has a weight force, right? It's going to have that weight. So I'm going to draw it like that. W for the weight of the cylinder. And we also know we have a cable, so we have a tension force. Note the tension force is going to act in the opposite direction because it's tension force is always pulling. It's always away, right? So it's going to be tension. And I believe that's all for this. So what does this mean? If you look at it with respect to equilibrium, the weight is equal to the tension, right? Sometimes we see that often, and you just have to know weight equals to tension. They must cancel each other out to have equilibrium. So now the AC, let's do AC now. The beam member AC. So we have that, and let me draw it like that. We have C here, C's here. We know at C we have a tension, right? We have a tension force, and with respect to that free body diagram, beam AC, it's going to act away, right? It will act away. Tension always acts away, so it's going to look something like that. And that tension in here is the same in here, but you just have to be careful and draw it away. It's the same idea, right? In this free body diagram, it was acting that way. In this one, it will be away. So now, also we will look at what's going on here. So we know in this diagram, it was like that. So tension's always away. So it would look like this in this diagram. And at B here, we know it would look something like that, tension. Then what else do we have? We know at A, we have what kind of connection? Pin connection at point A. So we know we have an AX and an AY. And that will be that free body diagram for AC. Let's keep going. Let's do the free body diagram of CD. Free body diagram of CD. So we're only looking at member CD. So for that one, we know we have point D here. And I know I have like a pulley, and that is going to get stuck to that part, right? Part CD. It's like a total segment, and it gets stuck to it, right? You can't really take that out. So what I'm going to say is draw a circle for that, for this portion. And we know here that we have a cable, so we have some tension here. And that same tension is going to be the same here, right? It's the same tensile force for that pulley tension. So that's done. And we know here there's like a dimension for this, which is not like given. But no, there's like that distance, which is like the radius. Let's say you want it to do equilibrium or take the moment about point C here. You have to have that distance, right? But no, that's just the radius of the pulley. So we have that. Then we know point B is here, and we have point C here. So let's do the easy one. Point C, we know it's a pin connection. So we only have a CX and a CY reaction. So that one's done. Now, this is interesting, and it will save us a lot of time. What do you call this member? There's a certain name we give that member. It's a two-force member. It's a two-force member, and always note a two-force member. Let me just draw two, like a segment here, and let me just label that A, B. A two-force member is always going to get loaded only at the ends. It only gets loaded at the ends. What that means is we know at B we have some reaction. Let's call it BX, BY. And we know at A we have a reaction. Let's call it AX, and we will say AY. And both of these are only loaded at the ends, right? And we know here when you have like a X component, Y component, you have a magnitude. And when you have a AY, AX, you have a magnitude force, right? And that magnitude force is actually the same. For a two-force member that are always only loaded at the ends, the magnitude force is the same. So we will approximate and say, okay, that magnitude force would probably look like this, and it's going to have the same line of action, right? It will always have that same line of action, and it's a force, and that force here, note, is the same as the force here at A. So that's why we call it a two-force member. And no, if it wouldn't be a two-force member if you had like a applied load hitting this thing, so it no longer becomes a two-force member. So always look for those two-force members only loaded at the ends, right? In this case at A and B, you have those reactions at A and B. So what does that mean? We know it's a two-force member, and what you can simply do is simplify this and draw the force like this. You can assume the direction and draw the force like that, right? It's a force at an angle, and you can probably, if you're given the dimensions, maybe it's a 3, 4, 5 triangle, you can break that down into respective components. So that's how you would draw that two-force member here that acts at B. So that's the quickest way to do that. We have a two-force member. So now we have this one going on, and this one's tricky because we have springs here in this one, right? And it's member AC that we want to draw the free body diagram for. So here, you have to imagine you have a force applied at A, right? Picture your finger hitting A with a force, and we have to ask, okay, what happens to this? What happens here? So you hit it with a force at A, and I would assume, okay, when we hit it down there with a force, this spring is going to stretch, right? We would stretch the spring by some distance. We call that the distance S. Sticking with the FE handbook denotation, it's distance S. So we would like stretch it by some distance S from the original unstretched length. So here you have to imagine now, when we stretch that by distance S, picture like us pulling down on this spring by distance S, there's going to be a reaction that goes up, right? You would have to have a reaction that goes up. If you can feel it, and you have to imagine with the point of view of the member AC or the beam AC, you would have a reaction that goes up. So it's an opposite reaction, right? It's going to be opposite with respect to the direction we stretched. So here I just want to summarize it. Anytime you stretch a spring, it's going to act in the opposite direction, and anytime we compress, it's going to act in the opposite direction. So here we know we stretched it this way, right? We stretched it this way in this direction, so it's going to act up that reaction. So let's draw that real quick. We know it's member AC, and we know at A we have the force at A, that's given. At B we know, we will say, okay, we stretch it, so it's going to act in the opposite direction. So it would act up for that one. So let me denote that as the force B, force in the spring at B, force B. And now, same idea here. We have the force pulling this way. We said this one we stretch, and when you stretch this one, what happens here? We're going to also stretch this, right? You can kind of imagine it as stretching like by a distance S, and it stretches in that direction. So we're stretching this, so we have a reaction, the force in the spring that the beam actually feels is going to act down. It will counteract that stretch. Think of that stretch as pushing it, and the beam is going to react, right? React with the spring force, essentially. So now we know at the C, it's the force at C, and it's a spring force. And spring force for both B and C is going to be given by this equation, Ks, right? K is the spring constant that should be given to you, and S is your stretch distance from the original unstretched length. And I want to say sometimes these things are compressed, right? When they're compressed, it's the opposite idea, right? You have from the unstretched length, or from the original length, sometimes we compress a spring. So that's why they're kind of complicated, but in this case, they're both stretched. And that's how you would draw that free body diagram for this one. And now I'll leave this up to you. So I'm getting tired here, but you have a crane and you have this beam. So I challenge you to draw the free body diagram of the crane. This one's interesting because you have a fixed end. And I'll tell you, okay, a fixed end, you always have 3 reactions, right? So I'll leave that to you. Fixed end at A, you have some counterweights. We call these the counterweights of the crane. You have one here at C, and you also have one here, we call that G2. So it's counterweight, keyword weight. And you have this main frame or the jib of the crane. That's going to be here. It has a weight, and you have some weight that we're trying to move or carry, right? So you can draw an overall free body diagram of this crane. And you also have this one, which is also kind of tricky because you have a hinge, right? And I just want to give you a hint. Anytime you have a hinge, split it at the hinge. Split it at the hinge. Then in this case we have, I even said AC and BC. You have two different free body diagrams. So you draw one for AC, draw one for BC, and use the same general idea we discussed above for those reactions. But this one's tricky because you have a hinge. So I'll leave this up to you. You can comment below, show us what you got, how you drew these. But I'll also attach a solution if you drop your email, and I'll send you the PDF of this with the corresponding solutions. And I hope this was helpful. Any questions, please let me know. Thank you.